Hey y'all, welcome back. Let's take a look at tonight's homework. Now we're starting a new unit, as you are aware of. We are graphing trigonometric functions. So this problem number one just has us sketch the parent functions for sine, cosine, and their opposites. So sine will start on the y-axis at 0. Now we went over this in the lecture. I'm not gonna go into a ton of detail here. I definitely encourage you to go back and look at the notes video that I've got posted to understand why the curve looks like this. But really, I just want you to kind of have an idea of what the graph is going to look like. So just a quick sketch here. I'm not even going to label anything. I might go back and continue more of this, but we've really just focused on finding what one period of these curves look like. Yeah, sine starts at equilibrium. Which for the parent function is just at 0. It goes up to the maximum, which is at 1. So like if you want to label this, you can say, hey, here's 1. And then it goes down back to equilibrium, down to the minimum, and then back to equilibrium. And this period will just repeat itself over and over again. So you can imagine just kind of copying and pasting that piece of the graph over and over again to get the full thing. I'm going to leave that there for now, and then when we're done with all these, I'll go back and kind of fill them all in. Because I think once you graph the whole thing, it gets a little muddy as far as like telling them apart. But if we just focus on one period or one cycle, it makes it a little bit easier to distinguish them. For cosine, we're going to start at the maximum, go down to minimum. Maybe I'll go back and label some of these points. So I just stay consistent here. So start at maximum, go down to equilibrium, down to the minimum, then we go back up to equilibrium, and then back to the maximum. So the cosine curve kind of does something like this. Wow. Let's see if I can make that look a little worse. I don't think that's possible. Okay, so we're starting with equilibrium, going down, coming back up. And we really want to make sure that these look kind of curvy. Don't make like a zigzag pattern. It's, I want you to understand that these sections are not linear. Okay, these should not come to a sharp corner and make like a little V shape. Now it should be more U-ish, okay, a smooth curve where there's no like sudden change in rate of change. Okay, so now if these functions are negative, the effect that has on the graph is the same as it has when you negate any function, which is it just flips the whole thing over the x-axis. Now when we're graphing these functions with transformations, instead of thinking about it as flipping it over the x-axis, we're just going to flip it over equilibrium because that would be sort of the net effect at the end anyway, especially if you're dealing with vertical shifts. So anyway, we're going to take this exact same sine graph over here and just flip it. So instead of going up, we're going to go down at first. So we're going to go down, come back up, and do something like that, with these being our 5 key points. Same kind of deal with cosine. Instead of starting at a maximum, though, we're going to start at a minimum. So we'll be down here. We're going to go up, go through equilibrium, up to the maximum, down to equilibrium, and then down to the minimum. Now I'm going to keep that, I'm going to leave that alone. I'm going to go back here and kind of fill out the rest of the graph. I'm going to use a different color just to make it easier to see how these are different. Because like I was saying before, if you just kind of do them all, then they all just start to blend together, I think, if you're not paying close attention. So, basically this little section is just going to repeat itself. So, it just has like this little wave pattern that just continues. Okay? Do my best to kind of curve this out. All right, same thing with cosine. You just have the same pattern going over and over again. And then same deal with these inverse signs. Not inverse, but negative signs. Yeah, we're not talking about inverse functions quite yet, although we will very soon. Oh man, I wish I could do this a little better. Again, we're not trying to make this perfect. We're really just trying to get the idea of what the graph should look like. I'm not really liking how this is turning out though. I'm really struggling here. That's okay. Now down here, starting with number 2, we're gonna be a little bit more careful about how we sketch the graphs. But up here, I just wanted you to do a quick little sketch on what each of these look like with a real focus on this little red part of it. So yeah, let's take a look at number 2. Now here's where we're getting a little bit more serious here. So As you go through these, we want to find different characteristics of the graph. So there's 4 characteristics that we're going to be looking at, and I'm just going to make myself a little template here and just copy it over and over again. But the first thing we're going to look at is amplitude. We want to know what the amplitude is. We want to know what the, let's see, what else is there? The period. We need to know the phase shift and the vertical shift. Now this is not exactly the order that I would typically find them in, and you'll see as we go through these what order I will usually go through. This is going to be too big. Let's make this a little smaller. Okay, and just to save myself a little bit of time here, I'm just going to copy and paste this for all of these. Oops. Because we're going to want to find these for every single one. So as a little reminder, the amplitude is found by doing the absolute value of whatever the A value is. Okay, so let's start with, now what I like to do, let's kind of just review this real quick. So when you have a function that's in the form y equals, there we go, y, oh gosh, let's change that color. It's going to be kind of hard to read there, especially right on top of there. All right, third time's a charm here. Y equals a, we'll just start with sine. It kind of works the same way with cosine. But let's say your function looks like this. So each one of these letters, A, B, C, D, are going to be different parameters that affect the graph in different ways. And this is something we talked about in the lecture video. Go watch that video if you want a lot more detail about how that works. But basically, the amplitude will be computed by finding the absolute value of A. Okay? The period is going to be 2 pi divided by B. The phase shift is going to be C divided by B. And the vertical shift is just D. So to me, the easiest thing to find is the vertical shift because there's no, you don't have to perform an operation on it, you don't have to calculate anything, it's just literally what are you adding to the function. And here we see we're not adding anything. Okay, that's different than this problem over here where we're adding 1. But you see we're not adding anything here, so the vertical shift is just 0. And so the first thing I'm going to label here is 0. Okay? It's going to be my vertical shift. Now, let's go back just 1 second before we start labeling other stuff. I just want to kind of get something down to give us some kind of reference here. But really, we could go through and sketch all these functions right away without even, looking at any of the parameters. And I think maybe that's going to be our strategy here. It's just to really get comfortable knowing what the graph is going to look like before you start changing anything. So the technique we used in class was to basically identify which one of these 4 graphs is it up here. Is it sine, cosine, or negative sine, negative cosine, and then plotting these 5 points accordingly. Once you have the points down, we can make the axes and the scale kind of fit our cycle. So this first one is a negative cosine graph. Okay, the A value is negative. That's going to cause that reflection over equilibrium. And so we're going to be basically copying this diagram up here, where we start at a minimum, and then we go to equilibrium, and then we go to the maximum, down to equilibrium. Ugh, terrible point. Okay, is this going to be one of those things? Okay, let's just try to get this. Maybe I just need a mouse pad. I don't know. Okay, so I'm going to go ahead and sketch this curve. I'm going to go up, back down. Notice I'm not even looking at the numbers yet. Kind of got ahead of myself with the vertical shift here. Okay, so let's go through and see, do we have any other negative cosine graphs? We've got a positive sine, positive cosine, positive sine, positive cosine. We got it. So yeah, that's the only negative cosine there. So that's the only one that's going to kind of look like this, like a little hill. So let's look at sine. This is a positive sine, so it's going to look like this guy over here, where we start at equilibrium, go up, come back down to equilibrium, down in the minimum. Come on now. Get in there. Okay, there we go. And then back to equilibrium. So our curve is going to go up. Let's try that again. Go up. Come back down. Ugh, gosh. Just really not happy with the way these curves are turning out. Okay. Let's see. There we go. All right, so there's sine. And actually, I can use this same thing for the other signs. So here's another positive sine. So I'm going to go ahead and copy that entire thing because it will be the exact same graph. That's kind of the nice thing about doing it, graphing it this way, is that all the graphs that you're going to draw for sine and cosine, they're all going to look like one of these four red images up here. But we'll go back and we'll label everything to make sure that it actually is accurate, depending on whatever the transformations are. Here we've got a positive cosine. So we're going to use like this little image right here as our cycle. So we've got a positive cosine that's going to start at the maximum, go down to equilibrium, go all the way down, and then all the way back up. And I'm kind of thinking what we can do is just kind of graph all 6 of these simultaneously. And what I mean by that is, once we get these sketches down, what I'll do is just kind of go through one characteristic at a time. And so you can kind of see how that is going to affect each one of these graphs. Now, this was a positive cosine. You see down here we've got another positive cosine. There's no negative in front of that, so I can use the same image. The graph will look basically the same. It'll just be, moved around somewhere on the coordinate plane. There we go. And then down here we've got a negative sine, so it'll be like this thing, but just flipped over equilibrium. So it'll be like this, where it starts at equilibrium, goes down, comes back up, and goes back down. All right, so let's see if we can get this to look halfway decent. Ugh, so difficult with this mouse. I know, you guys are probably tired of me complaining about all my woe is me problems trying to graph this thing, but what else am I going to talk about here? All right, so there we go. Okay, so all the graphs are done here, basically. Now comes kind of the tricky part. All the graphs look the same, but we do need to label the x and y scale and include the x and y axes in the sketch. So there's like 2 other things that we need to do here. Okay, so first, let's focus on kind of labeling here, and we'll put the x and y axis at the end. Okay, so let's run through all of these vertical shifts, because the vertical shift is going to tell us exactly where equilibrium is, which is like this middle horizontal line. So the vertical shift on this next one, notice how we're adding 1 here, so that's just going to be 1. The vertical shift on this third one, we're not adding anything, so that's just going to be 0. So we could put a 0 here. And I forgot to put the 1 over here. There we go. For this fourth one, the vertical shift is going to be 0. Can we make that a little bigger so it can fit? There we go. You can see we're not adding anything here. This next one, we are subtracting 1. So that means that our vertical shift is -1. Just one little space in there, make that easier to read. Okay, so that means that our equilibrium should be at -1. And for this last one, the vertical shift is just 0. We're not adding anything. So let's label that. Okay, so like I said, the first thing to do is to get the actual curve drawn on there. Figuring out is it sine, cosine, negative cosine. Then do the vertical shift. Then what I like to do next is the amplitude. Okay, so the amplitude is going to be the absolute value of this coefficient. So the amplitude's never negative. So really, whatever the coefficient of your function is, that's the amplitude. So I'm just going to write them all out here. That's going to be 3. Absolute value of -3 is 3. The amplitude here is just going to be 1. Let's make this a little nicer. The amplitude here, you can see, is 1/2. The amplitude for this one is 2. The amplitude for this one down here, no coefficient here. There's a 1 there. That's just sort of implied. And same thing for here, 1. It's not going to be -1. Remember, the amplitude is always positive. It's the absolute value of A. Okay, so what we do with the amplitude is telling you basically how far the extremes, the maximum and the minimum, are from equilibrium. Like how far up does the wave go and how far down does the wave go. So if the amplitude is 3, like in this case, we're going to add 3 from equilibrium to go up and subtract 3 to go down. So now my vertical axis is done being labeled. This tells me all the information I need to know. We haven't put the axes on yet, but we'll do that last. The amplitude for this one is 1, so I'm going to add 1 and subtract 1. Notice here the x-axis is going to be down here, and this minimum is going to be 0. For this next one, the amplitude is 1/2, so I'm going to go up 1/2 and down 1/2. A little bit of a vertical compression there. For this one, the amplitude is 2, so I'm going to add 2, subtract 2. For this one, I'm going to add 1, so -1 plus 1 is 0. So actually here, the x-axis is going to be up here. And then I'm going to also subtract 1. So this whole curve will be below the x-axis. And then this one over here, amplitude's 1, so we're going to add 1, subtract 1. Okay. So the next thing to do is identify the phase shift, because the phase shift is going to tell us where this window or this cycle begins. The phase shift is computed by doing C over B. Okay, so it's the C value. If you're not adding or subtracting anything inside the parentheses, then the C is just going to be 0. So it'll be like 0 divided by whatever this number is. And I'm looking through these 6 problems. I actually don't see, I don't see any C's. Right? There's no number being added or subtracted inside any of these parentheses. And we're going to see some more of those, again, sorry about the pun there. We're going to see some more of these next time, some more complicated ones that actually do have a phase shift. But for today, it looks like all 6 of these, maybe there's a phase shift later on. Yeah, we've got a couple phase shifts. But for right now, the phase shift is just going to be 0 on every single one of these. So I'm just going to put that in. Phase shift is 0 for each one of these, and that's kind of nice, and it's going to make this a little easy. That's going to tell us that each of these windows are just going to start where the y-axis is. Oh, it's turned blue for some reason. Okay, so since the phase shift is 0, we can go and label this horizontal axis, and just each of these windows starts at 0. And that tells us that our y-axis is going to be in the same place for all of these curves. But we'll do the x and y-axis at the very end. Okay, so the last part is the period. So the period is found by doing 2 pi divided by b. And so we do need to note what the b value is, and then just compute it. So one thing I want to do here is I want to just type pi so I can just copy that easily. Oh, I thought I deleted it. Trash. Oh, come on. Stop disappearing on me. There we go. Okay, so the period, the parent is going to be 2 pi. It doesn't like that. So normally it'd be, well, that's very big. Let's try to make that a little smaller, shall we? It's a little too big. There we go. So it'd be 2 pi, all over b. For the parent function period is 2 pi, because if you don't have a coefficient here in front of x, it's just going to be assumed to be like 1. Just like for any variable, if you don't see a number in front of it, it's assumed to be 1. So if this is just 2 pi divided by 1, then it's just going to be 2 pi. Okay. Oh, did this freeze on me? Nope. There we go. So what I do with the period is the length of time it takes to complete one cycle. So like from the beginning of the window to the end, that distance is going to be 2 pi. Normally what you would do is you just add whatever the period is to the phase shift to figure out where the end of the window is. But since we're just adding to 0, the period is just going to be the end of this window. But don't think that that's always going to be the case. okay, it is 2 pi plus the phase shift. It just so happens that on all these that we have so far, that the phase shift is 0. Like I said, next time we'll look at some more complicated ones. So there we go. So all the labeling's done here. Let's finish the labeling on the rest of these, and we'll do the x and y axes. So the period for this next one is going to be 2 pi divided by b, and again, we have no coefficient here. So it's just a 1 right here. So that's going to be 2 pi divided by 1 is 2 pi. So 0 plus 2 pi is 2 pi, so the end of my window is 2 pi once again. For this third one, 2 pi, now we do have a coefficient here. We actually have something a little bit different. We've got 2 pi divided by 2, because our b value is 2 here. So 2 pi divided by 2 is going to reduce. These 2's are just going to reduce to 1, and so our period is actually just pi. Whoa, what happened to my graph over here? What the? Okay, it's all right. We'll make it work. Anyway, we just get pi here. And so we have 0 plus pi is pi. Now all of a sudden, I don't know what I pressed, but my sine graph went away. Luckily, I can just take this, copy and paste it down here. Okay, so here we've got 2 pi divided by 1/2. A little tricky here, but dividing by 1/2 is equivalent to multiplying by 2. So here, the period is actually 4 pi. This is a horizontal stretch. So yeah, the end of my window here is going to be 4 pi. And then for this cosine x minus 1, the period is 2 pi divided by 1. So again, we get just another period of 2 pi. So I'm going to say 0 plus 2 pi is 2 pi. And then for this last one, the period is going to be 2 pi divided by 3. So that's kind of annoying, but it's going to be 2 pi divided by 3, so 2/3 pi. Luckily, we are adding to 0, so we don't have to get lost in any kind of fraction addition here. But if it wasn't 0, that one would be a little messier than the rest of them. But it's okay, just label it, and we're good to go. The last thing to do here is to throw down the x and y axes, right? We want to include the x and y axes on the sketch. We already labeled the x and y scale here. So the x-axis for this first one is going to be right here, and the x and y axis are going to be where x and y are 0. So, so wherever y is 0, we'll have our x-axis, and wherever x is 0, we'll have our y-axis. So there's your x and y. And I might just throw on a little y, a little x here, make it really obvious what these lines are supposed to be. So there you go. There's one cycle of the graph of cosine, -3 cosine x. Here we've got our x-axis is actually down here, and our y-axis is here. So this whole graph is actually this wave is kind of riding the x-axis down here. Here's y, here's x. For the next one, it looks like we've got, this is a pretty standard place to put the axes. If you don't have any shifts going on, it's usually going to look like this. So here's my y-axis, here's my x-axis. Let's see, for the fourth one, our x-axis is right here. Yeah, so same place as the last one. Here's y and here's x. For this one, yeah, actually our x-axis is up here, and our y-axis is right here. It looks like the y-axis, yeah, the y-axis is going to be in the same place every time because we didn't have any phase shifts. Okay, so here's my x, here's my y, and my x is over here. So this whole wave is going to be going up and down all below the x-axis. And then for this last one, we have sort of the, the parent, well, one that's similar to the parent function. The only difference here is this is going to be a vertical compression, and also the reflection, I guess. So here's the y and the x. Okay, so there's those 6 graphs. I know there's a lot going on there, but hopefully you could see as I go through like each individual characteristic, you know, sometimes it's easier when you're graphing a bunch of them to just like do one thing at a time for all of them. So like, you know, draw your curves, sine, cosine, negative cosine. Then after you get the curve drawn down, find the vertical shift, then find the amplitude, then find the phase shift, and the period last. Okay, so let's move on. We are just identifying the things that we already found up here in these graphs. We're just not going to graph it. I'm just going to calculate what these are. So let's, whoa. So what I'm going to do here, you know what, let's copy this. I'm just going to give myself like a little answer bank, basically, or a place to put, not copy, a place to put all my answers here, so I don't have to just keep typing this over and over again. I don't know what's going on with this blue box over here. Okay, so let's just knock them out one at a time. Amplitude is the absolute value of A, so that would just be 5. The amplitude here is just 1. Amplitude here is going to be 3/5. Here it's going to be 1.4. Here, be careful, it is going to be 2. It's the absolute value of A, so you can just kind of ignore that negative sign. The amplitude here is going to be 1. Okay. The period is 2 pi divided by B, so this would be 2 pi divided by 1, so that's just 2 pi. Let me steal a pi up here. We're going to have that. So here we've got 2 pi divided by, 1/7. So dividing by 1/7 is the same thing as multiplying by 7. So that would be 14 pi. Here we've got 2 pi divided by 9. So it's just going to be 2 pi over 9. Okay, and you can't really reduce that or anything. Here we've got 2 pi over 3. Okay. For right here we've got 2 pi over 0.4. Okay, so I gotta do some mental math here. So 4/10 is equivalent to 2/5. So what we really have here is 2 pi divided by 2/5, which is the same as multiplying by 5/2. Okay, so just kind of follow me here. So 0.4 is 2/5. If I'm dividing by 2/5, it's the same as multiplying by 5/2. So 2 times 5 is 10, divided by 2 is 5. So our period is going to be 5 pi. Here we've got 2 pi divided by 1.8. Okay, so 1.8 would be, let's see, 8/10 would be 4/5 plus 1 would be 5/5. So that'll be 2 pi divided by, let's see, so 5 and 4 would be 9/5. Now I'm really putting my fraction skills to the work here. Okay, so 2 pi times 5/9. Okay, so 2 times 5 is 10, divided by 9. You can't reduce that, so it's just going to be 10 pi over 9. Yeah. All right, let me clear all this out of the way. Okay, so there's all the periods, the 2 pi divided by B. Now let's do the phase shift, which is C divided by B. So this is going to be just 0, okay, because we don't have any C. This one's also going to be 0. We're not adding or subtracting anything in the parentheses. That's what we're looking for here. This one's also 0. This one, okay, now we've got something to work with. So you want to be careful with the phase shift. You got to be careful here. So this number right here is actually -1, okay? Because let's go back to like the actual format here is bx minus c. This is something you had to worry about in Algebra 2 as well. But basically, this is the only, these B and C are going to do kind of the opposite of what you see. So, not the opposite, but, well, let's just focus on the phase shift here. So whatever number that you're going to see here, it's actually going to be the opposite. So this is the C value is actually -1 here. So we get -1 divided by 3, so -1/3. Here we've got 0, and here we've got 2 divided by 1.8. Now, I haven't really used a calculator yet. I'm not going to be mad if you use a calculator to reduce that, but I think you could probably do it. 2 divided by, what did we say it was? 9/5. So that'd be 2 times 5 is 10 divided by, so it'd be 10/9. Okay, we can double check that in the calculator. Might as well throw it in there just so I don't write down anything that's wrong. But we got 2 divided by 1.8. What? Oh, okay. 2 divided by 1.8. Oh, come on. Click those buttons. And then let's see what that is as a fraction. And yeah, it's 10/9. Okay, so if you put 2 divided by 1.8, that's not wrong. It's just not, you usually don't want to have decimals in your fractions. So yeah, let's just change this to 10/9. All right, so the phase shifts are all done. Vertical shift, usually the easiest thing to do is just whatever you're adding to the function. And it looks like only one of these is going to have a vertical shift. This one's 0, this one's 0, this one's 0, 0. The only one is this letter F that actually has one, and it's going to be 5. That's it. Okay, so we got the amplitude, the period, the phase shift, and the vertical shift. For all these, yeah, and we could use these to graph. I mean, we'd graph them basically just how we did up here. And now that we have all the information, it should be pretty easy to find them, actually. Last thing is just graphing, okay? So here, this is about the extent that I want you to be familiar with these graphs, okay? I just want to make sure that you know what they look like in general. So the way that I like to think about it, I start with tangent, I think. Okay, well, on the unit circle, let's just pull up the unit circle real quick. At 0, okay? At 0 radians, you see the coordinate is 1, 0. So tangent being y over x, just a little reminder here, would be 0/1. So what I'm looking for tangent is the y-intercept to be 0. And we can see that's occurring right here on D, okay? So we're going to say this is D. Cotangent is the reciprocal of that. So wherever we have a 0 for tangent, we're going to have an undefined, a vertical asymptote. You can see that's happening on choice B here. And vice versa. Wherever we have a vertical asymptote for tangent, we should have a 0 for cotangent. So you can kind of see that these two graphs are related and they are reciprocals of each other. So the cotangent one should be B. So that narrows us down to A and C for secant and cosecant. So let's think about what's happening when we have 0 radians. So let's start with, let's say, secant. So secant is the reciprocal of cosine, right? So we're looking to see what is the cosine of 0 radians. So I look at my unit circle, I know cosine's talking about the y value, the x value of the coordinate on the unit circle. So I see up there, that the x coordinate is 1 at 0 radians. So that means that secant should have a y-intercept of 1. And we can see that that's this one right here. So this is going to be C. And then the last one must be A. Let's get rid of that unit circle so you can actually see those answers. That's it. Okay, so just make sure that you can do something like this where you can identify which graph is which trig function. We're not really going to spend a lot of time graphing these 4 other functions. All of our efforts are really going to be going to graphing stuff like this and then slightly more complicated ones that have phase shifts and stuff like that. We're going to practice this a lot more next time. This is just kind of an introduction. I want to throw everything at you, and then we're going to kind of put it all together and practice more in our next lesson. So you all have a great day, and I'll see y'all next time.